As we come to the end of our study of limits and continuity, let's go back to the start and look at average rates of change again and see how they're going to lead us to the concept of tangent lines. There are a lot of average rates of changes around us. Our average speed, measured in miles per hour, growth rates of population, often measured in percent per year, a 5% growth per year. And we also would have something like maybe monthly rainfall would be another example of an average rate. Measured in inches per month. So the average rate of change of a quantity over a period of time is going to be the amount of change divided by the time it takes. In general, the average rate of change for a function on an interval would be the amount of change for that function divided by the length of the interval. So let's take a look at an example here. Find the average rate of change for f of x equals x cubed minus x over the interval from 1 to 4. Well, this function at 1 has a value of 0. At 4, that'd be 64 minus 4, value of 60. So the average rate that's a v, is the change in the y or the change in the x. So in this case, the y, 60 minus 0, and the change in the x, 4 minus 1. So we have 60 over 3. The average rate of this function is 20. So for this particular function, it's saying that every time x goes up by 1, the function value goes up by 20. Now notice here that an average rate is found by taking delta y over delta x, change in y over change in x. We know that this change in y over change in x is what we often call the slope of a line. So this 20 somehow represents a slope of some line associated with x cubed minus x. And that's what we're going to look at and examine in more detail here. So we're going to find the slope and tangent line for the parabola y equals x squared at the point 2 comma 4. We're going to write an equation for the tangent to the parabola at this point. So let me draw a part of the parabola. Okay, let's call this 2. There would be our point. That would be 4. Let's call that point P. So we're interested in finding the slope of the parabola at that point. Well, we calculate slope by using 2 points and performing a subtraction. Well, here we just have a single point, the point 2 comma 4. So what we're going to do is we're going to choose another point on the curve, just a little bit further to the right of it, or even perhaps to the left, but we'll use it to the right in our diagram. 2 plus some value of h, a small value of h. And that point would be about here. Let's call it Q. And the value over here is going to be, let's see, we put 2 plus h into y equals x squared. We're going to have 2 plus h squared. Now that I have 2 points, I can calculate a slope. And the slope would be the slope of this particular line. Notice there's some space here between the line and the curve. So the line is not a tangent line because it intersects the circle in more than one, intersects the graph in more than one place. And this line is what we call a secant line. So we're going to find the slope of the secant. Again, it's going to be change in y over change in x. Well, the y values are 2 plus h squared subtract 4. And the corresponding x values would be 2 plus h subtract 2. If we multiply out the numerator, simplify the numerator and denominator. In the numerator, 4 minus 4 is 0, so we have 4h plus h squared. In the denominator, we have an h. The numerator has a common h factor, so I'm going to extract that factor. So the factor of h in the numerator reduces with the factor of h in the denominator to 1. So the slope of our secant is equal to 4 plus h. So if our h value is 0.01, the secant slope would be 4.01. If our h value is 0.001, the slope of our secant would be 4.001. Now we want the slope of the tangent. And to find the slope of the tangent, we want the line that intersects right there at that single point. What we can do is allow point Q to slide closer and closer to point P, and our secant line is going to approach becoming our tangent line. So what we want in this case is we want to take the limit of the secant slope. What's the secant slope approaching as the h value approaches 0? Because as Q moves closer to 2, or to P, 2 plus h is moving closer to 2, and that only happens when h approaches 0. So we're looking at the limit as h approaches 0. Well, in this case, the secant slope is 4 plus h, and that limit turns out to be 4. So the slope of the parabola at the point 2, 4 is 4. To find the equation of the tangent line, we have our point, we have our slope of that tangent. The slope of the tangent is 4. It passes through the point 2, 4. So our equation is going to be y minus 4 equals 4 times x minus 2. And in AP, that's perfectly fine to leave it that way. The only time we'd want to change it and solve for y is if we need to put this into a calculator for some reason. You can check all this by graphing y equals x squared, and then graph y equals 4 times the quantity x minus 2 plus 4. We should see that the line does appear to be tangent to y equals x squared at the point 2, 4.